Right, so we've got this reaction. Don't worry so much about the reaction equation itself. It's what you're really interested in is this rate equation. So what's that telling us is that the order with respect to hydrogen is first order, and the order with respect to nitrogen monoxide, NO, is second order because of the power 2. Okay, so basically the rate is proportional to the changes in concentration raised to the order power. Okay, so what's the rate going to do? Well, it says that the hydrogen concentration is halved, so that halving of the concentration for hydrogen needs to be raised to the power 1. Okay, so this is for the hydrogen, and then that gets multiplied in the rate equation, doesn't it, by the nitrogen monoxide concentration. So what's happening to that? That's getting doubled. Okay, but that's second order. Okay, so 2 to the power 2 is 4, half to the power 1 is a half, so in other words that's a half times 4, which is 2. Hi. So therefore the overall rate is going to double, so the answer was C. Okay, I hope that all made sense. So whatever you do to the concentration, if it's first order, the rate will go up by the same or change by the same factor. If it's second order, it will change by the change in concentration squared. Okay, so we had, I'll just put the NO in there. So we had the hydrogen was halved, so it's a half to the power 1 times the doubling in concentration raised to the power 2. Okay, so that overall is that, gives you the 2. So the answer was C. If there's any questions, just fire them into the chat and I will keep an eye on the chat and see what people are asking. Okay. Right, the next question is the reaction 2AB going to 2A and B2 is first order with respect to AB. The half-life of the reaction is 2 minutes. Okay, so the thing hopefully that you've learned from the notes is that first order reactions have constant half-lives. Okay, constant half-life. So basically every 2 minutes the concentration will halve from the value that it was originally at. Okay, so notice this is given in moles. Okay, so we've got 0.1 moles of AB and it's been dissolved in a volume of 100 cm cubes. Okay, and we want to know the concentration. So I think some people tripped up on the fact that they calculated the final moles but didn't turn it into a concentration, and unfortunately for you the final moles is one of the options. All right, so obviously they're going to do that because they know a lot of students are going to do that. Okay, so the way I did it was I kept it in moles. All right, so the original moles is 0.1. okay, so I've just got like a number line here, so 0.1. So after 2 minutes, this is your first half-life. After 2 minutes, the moles, sorry, not the concentration, the moles is going to go down to 0.05. Okay. After another 2 minutes, so we're at 4 minutes now. That's 2 half-lives, isn't it? We're going to go to 0.025, so halving again. So after another 2 minutes, so we're now at the 6 minute mark, this is where we want to be, we get to 0.0125. But remember, these are moles. And you can see there's an option there for 0.0125. And a lot of people actually selected A as the answer, which is not correct, unfortunately. Okay, so the concentration is therefore the moles after 6 minutes, 0.0125, divided by the volume in decimeters cubed, which is 0.1, and that gives you 0.125 moles per decimeter cubed of a concentration. So the answer was C again. Okay, so that's that one. So there's a couple of things being tested there. Obviously, your knowledge of first order reactions having this constant half-life, and then obviously understanding what that means, concentration or the moles half every set amount of time, which is the half-life. And then the little nasty twist at the end was turning those moles into concentration. You've got to be really careful. You check all the wording and that you sort of know exactly what they're after. Okay, so that was that one. So number 3, I suppose was a little bit nasty of me to put this in because we haven't done the transition elements, okay, where you would have known the answer. All right, so, but I was thinking that maybe some people might know a little bit about copper sulfate. Maybe you did some research onto it. That is also possible for homeworks, isn't it? But anyway, let's look at the equation first. So zinc reacts with copper 2 sulfate solution. So Zn plus CuSO4, so GCSE reaction this. And you get a displacement reaction taking place where you get the zinc sulfate produced and the copper's displaced. Okay, so the first thing is, can you use a balance to monitor the rate of this reaction? Well, no, because you can see there's no gases produced, so the contents of the reaction flask or whatever you carry it out in is not going to change. So you can't use a balance. You can't use a gas syringe for the same reason as before. No gases are being produced in this reaction. Okay, I'm going to jump to the other wrong answer. pH meter, so there's no H plus ions, okay, in this reaction mixture, and so therefore the pH isn't going to change. So we couldn't monitor the pH. So obviously colorimeter is the only one left. So why is colorimeter the right answer? Well, this chemical here, copper sulfate, is blue. So that would be a blue solution because it says aqueous. Okay. Zinc compounds are colourless. All right. So that will be a colourless solution. So basically, as this reaction proceeds, the blue solution is going to fade away, the sort of strength of the colour. Okay. Now you could monitor that by a colorimeter. Okay. And colorimetry is, so the colour of the solution is directly linked to the concentration. So the more concentrated this copper sulfate is, the more intense the blue colour is, and obviously a colorimeter could enable you to determine all of that. So that is why option C was the right answer. So these questions, by the way, from different exam papers, it just so happens that the 3 on that page have all got C as the correct answer. Okay, I hope people weren't choosing like C just thinking, can't be C again, I better choose something else. You know, you just don't know what's in the exam board's head when they put these questions together in terms of the options. So hopefully that made sense why it was C. Okay. Right, number 4. So I was really impressed actually with people's attempts at this. The only issue was there was a couple of people, or there was a few people who lost marks by just missing out simple little things that you've got to watch out for. So that was the first thing. I did notice a couple of people struggling with the mechanism, which is probably, in my opinion, I think the mechanism's the trickiest bit of the rates topic. So I'll just go very carefully through this. Right, so what have we got to do? We've got to determine the rate constant, so obviously that's K, isn't it? And a possible two-step mechanism for this reaction that is consistent with these results. So your response should show clearly, show how your calculations and explanations are linked to the results. Okay, so I'll pick all that out as we go through the answers. Right, so if we're going to work out K, we've got to work out the rate equation. And to get the rate equation, we have to work out the orders of reaction with respect to the two reactants. So that's the first thing. So we've got these initial rates, this initial rates table, and I don't know if you've noticed, but I've posted a PDF of lots and lots of these questions onto Google Classroom for you, and the answers as well, so you can get lots of practice at this if you need it. Okay, so I would strongly recommend that everybody does it, to be honest, not just people who think they need it. Right, so what we're going to do, we're going to look at, let's go for experiments 1 and 2. So you can see that the NO2 concentration is being kept constant at 2.5 times 10 to the minus 3. Right, so this trebling in concentration of ozone is affecting the rate, because you can see it's changed. Right, so what I would strongly recommend you do is do a sort of arrow like that. Okay, so that's telling the examiner you're looking at those two experiments, 1 and 2. I would write there times 3, because that's a trebling in concentration. And then go like that. And you can see that 3.2 up to 9.6, obviously times 10 to the minus 8, is also a trebling. Okay, so that's, you could argue that that's not particularly clear. So what I'm going to say is from 1 and 2, the O3 concentration times 3, rate times 3. So I'm just putting what I've my annotations in the table into words. Therefore, it's first order with respect to, you can put WRT, O3. Okay, so that's nice and clear for the examiner. They're not going to struggle with any of that. That makes perfect sense. Okay, so let's move on to the order with respect to NO2. So we need to keep the ozone constant if we can, and we can in experiments 2 and 3. So you can see in experiments 2 and 3, the ozone's kept at 3 times 10 to the minus 3. So that's the right set of experiments to use. So you can see that going from 2.5 times 10 to the minus 3 up to 5 times 10 to the minus 3, that's also a doubling. And now it's not as easy to see this, so you just take the big number and divide by the small number. So 1.92 times 10 to the minus 7 divided by 9.6 times 10 to the minus 8 is a doubling. And so therefore that is also first order. Okay, so we'll just put that into words. From 2 and 3, concentration of NO2 is times 2, rate times 2, therefore first order with respect to NO2. So we've got both the orders. We can write the rate equation now. Therefore, rate equation, rate, remember they all start, rate equals K, and then we have square brackets, O3, and you can put a multiplied sign, and if you want, I don't bother, I just have them next to each other, multiplied by NO2, and that's it. That's the rate equation. Okay, so to calculate K, we need to rearrange this, make K the subject of the equation. So K equals rate divided by O3 concentration times NO2 concentration. So I'm going to take row 1, could take any of the 3 experiments, but I'm just going to use row 1. Okay, so my rate for experiment 1 is 3.2 times 10 to the minus 8 divided by 1 times 10 to the minus 3 times 2.5 times 10 to the minus 3. And that comes out at, how much room have I got left? That comes out at 0.0128, 3 significant figures. Okay, so that's the numerical value for K. What we need to do now is work out the units for K. So I'll just change to red. So the units for K, just show you where they come from. So the units of rate are moles per decimeter cubed per second. So they're on the top. And we've divided that by moles per decimeter cubed times moles per decimeter cubed. So I'll write them both out. So I'm literally just putting the units of these things into an expression, and then I'm going to cancel what I can. So I can cancel moles per decimeter cubed on the top with one of the ones on the bottom. What am I left with? I'm left with seconds to the minus 1 on the top, and I'm left with one lot of moles per decimeter cubed on the bottom. And then we take all the terms should on the bottom need to go up to the top, and all we do is flip the sign of the power. Okay, and if we do it sort of conventionally, we should put the positive power first, but you don't have to. So the dm to the minus 3 becomes dm cubed. Mol to the minus 1, seconds to the minus 1's already on the top, so they needed to be in there as well. Okay, but if you notice, they didn't ask for them in the question, but they expect, you know, a good student would know that the K value needs units. So that's kind of used as a differentiator between sort of a good student and maybe not as good, you know, a student. I know it's an awful thing to say, but that's what they do. Okay, so that's the sort of numbers bit finished, the calculations done. And now we've got to come up with a possible two-step mechanism. Okay, so the way I do it, I sort of tabulate it, if you remember. I'm going to write the overall equation at the bottom. So it was O3, 2NO2. So overall this is O3 plus 2 NO2s goes to, what was it again? N2O5 plus O2. Oops, N2O5. Okay, and we need 2 steps. Okay, so step 1, step 2. Right, now a couple of people lost marks because they didn't clearly show which one was their rate determinant step. Okay, so let's just have a look at where we go from here. Right, the rate equation, I'm just going to highlight that, that's really important. The rate equation tells us the chemicals involved in the rate determinant step. Okay, so let's make the rate determinant step step 1. Okay, so next to that I'm going to write RDS. So I'm making it clear that that's my rate determinant step just by writing RDS next to step 1. The fact that we've got an O3 order 1 and an NO2 order 1 in the rate equation means that our reactants for step 1, the rate determinant step, has got to be O3 plus NO2. That is all we're allowed as reactants for our rate determinant step. Okay, right, so the way my mind works with this is I'm going to look at the overall equation, Now I need to make N2O5 and O2. Can I make any of those from our reactants in step 1? Well, I can't make N2O5 because I've only got one nitrogen. Okay, so I'm going to have to, but I can make this O2. So let's make the O2. So what have I got left? I've got an NO2 and an O left from this. So let's stick that together and we'll make an NO3. Okay. Now the NO3 does not feature in the final equation, the overall equation, so I need to get rid of it, and I do that by making it a reactant of the other step, step 2. Okay? Right. Now, what else do we need to get? Let's have a look at, I need 2 moles of NO2 when I add the 2 steps together. Now I've only got one at the moment, I've only got that one there. So if I put an NO2 as a reactant in step 2, that's given me the extra NO2 I need. And what can I do now? I can make the N2O5, because I've got 2 N's, I've got, in fact that's perfect there, because that's just going to make N2O5, isn't it? Okay, so that's a possible mechanism. And then what can we do? We can just show that when you add these 2 steps together, so when you add step 1 and step 2, you get the NO3s cancel out, and you basically get O3 plus those 2 NO2s makes O2 and N2O5. So that is consistent with the rate equation. Okay, so that's fine. I'm going to show you another way to do it, which somebody did, which I was really impressed with. So let's just do that. Get rid of all this, because there's often more than one way of doing this. Right, so what the other person did was they took the O3 and the NO2 and they made NO5. Okay, NO5, they just added everything together. And then obviously NO5 does not appear in the final equation, so they made it a reactant of step 2. And they brought in the second NO2 that they needed. And when you combine those 2 chemicals together, NO5 and NO2, you can make N2O5, and you're left with O2. And then cancel the NO5s, and you're left with the final equation. O3 plus 2 NO2s makes N2O5 and O2. So well done to that person for working that one out, that's great. And that's that. Any questions? Does that make sense? Anybody want to ask any questions on that one? Okay, we'll move on. If something appears in the chat, I'll go back to the question. Right, using the graph, what is the value of the pre-exponential factor A for the decomposition of N2O5? Okay, so if you notice this x-axis, that's great to hear, Georgina. Can I suggest if you noticed, I posted some extra sheets for you, some extra PDFs. So there's some, obviously there's my videos on rate determinant step, okay? But if you find the PDF, just go into Google Classroom, look in the rates section, and there's a PDF of loads and loads of rate determinant step mechanism style questions. All the answers are there for you as well, so try them over the summer, just make it part of your routine, and hopefully that'll sort everything out, okay? But that goes for everybody, not just people that found it difficult in the homework, Right, so Arrhenius graph now. So you'll notice that our x-axis actually starts at 0. Okay, so what that means is that the y-intercept is equal to ln of A. Okay, so that means that the ln of A is equal to 31.5. So where did I get that from? I literally just worked out where the graph was cutting the y-axis, obviously, and the scale's fairly easy to read, hopefully. 31.5. Okay. Now you'll notice that they're playing, they're playing with your minds a little bit. There's an option of 31.5 as an answer, but remember that's the ln of A is 31.5. We want what A is, not the ln of A. So therefore, how do you work out what A is? If you know the ln of A equals E to the value 31.5, okay, and that comes out at 4.79 times 10 to the 13. So you can see it was option D. So D was the answer for that one. Okay. Nearly finished. Right, okay, final page. 2 more multiple choice questions. So we've kind of already had this question. It kind of has already been tested, the theory here. The reaction below is first order. That's the key bit there. First order with respect to A. Okay. When the initial concentration of A is 1 mole per decimeter cubed, the half-life is 20 minutes. What is the half-life when the initial concentration is 2 moles per decimeter cubed? So they've doubled the concentration. Yep. So obviously some people are going to think double the concentration, first order, double the half-life, and go for the 40 minutes option, which is the wrong thing to do. If a reaction is first order with respect to a reactant, the half-life is constant. Okay? We've already seen that in this homework, constant half-life. Therefore, it doesn't change and it's still 20 minutes, even though the concentration's doubled. So B was the answer for that one. Okay? Okay. Final question. Final question of the year, in fact, because there's no more homeworks after this until September. You'll be pleased to hear. Right, so let's have a look at what's important in this question. Nitrogen dioxide reacts with carbon monoxide as shown in the equation. Right, okay, so we've got an equation. A proposed mechanism for this reaction is shown below. Okay, so we've got a slow step and a fast step. So the important thing there is that fact that they've said that's a slow step. That means that this step is the rate determining step. Okay, so the rate determining step, the reactants basically tell you what the rate equation is. So the reactants, there's only one type of reactant, NO2, but there's 2 moles of them involved. So that means that it's second order with respect to NO2. Okay, so this here is saying that it's second order with respect to the NO2. That's the only reactant in the rate equation, and so therefore the only possible option was C. Okay, so obviously the issue with A is the fact that it's not squared. It's got to be squared because we've got 2 moles involved, 2 molecules involved. It can't be B because there's carbon monoxide involved in that. Well, there's none in the slow step as a reactant. Obviously that is the right answer, and the reason we've just given for that one being wrong is the same reason that one's wrong. There's carbon monoxide there, but there's not in that slow step. So that's why C was the answer.